Hi, this is Professor Jen-Mei at Cal State Long Beach. In this video lesson today, we will introduce some of the essential components for simple algorithms and give a few examples along with their MATLAB implementations. At the end, we will introduce the big O and the little o notations to describe functions sharing the same limiting behaviors. In general, there are two types of computer softwares. They're symbolic and numeric. The MATLAB software that we use for this class is considered as a numerical implementations or numerical softwares. And the differences is really how the computer software manipulate expressions that we put into the system. The symbolic software, such as Maple and Mathematica, works really well with symbolic forms, dealing with functions and some of the abstract stuff, such as groups. Typically, when we write algorithms, it needs to satisfy the following 5 criteria. An algorithm is a procedure of a finite set of well-defined instructions that is meant to accomplish some task. You have to give it an initial state, and the algorithm needs to terminate in a definite end state. The first requirement an algorithm has to have is finiteness, which means the algorithm must terminate after a finite number of steps. The second condition needs to have is definitiveness. Each step must be precisely defined, and the actions needs to be carried out rigorously and ambiguously. You cannot tell the algorithm to do something that is ambiguous, and because that is because the computer can't make that decision on its own unless you tell it to. The number 3 condition it needs to have is input. Quantities that are given to the algorithm initially are considered as an input, and that's basically how the computer knows where to start. Fourth is the outputs. Quantities that have specified relation to the inputs are considered outputs. Number 5 is the effectiveness. Operations must be sufficiently basic and can be done exactly and in a finite length of time, even if it's done by a person using pencil and paper. So you can't have the algorithm run forever. In the next example, I'm going to illustrate a thought process that you should try to exercise when you or encounter a programming problem. You start with a recipe, and everybody's recipe is going to be a little bit different, just like when you're cooking a pasta dish. You might cook the noodle first, you might add the salt in the beginning or at the end. You might cook your sauce a little bit differently, and then you might put your noodles in the sauce right afterwards, or you wanted to separate them when you serve them. It's all a little bit differently, but the end result is the same. It's a pasta dish. Okay, so that's the first thing you need to start as a recipe. And then we're going to look at something called the pseudocode, which is kind of in between a strategy and your end result, because everybody's going to implement their algorithm on a different platform. Some people do it in MATLAB or Python or Java. It all depends on what you're familiar with. Also, the pseudocode gives you a language to then work with in your particular platform. And because in this class we're using MATLAB as our platform, we're going to show, for that example, a simple or just a sample MATLAB code that you could use. In this example, you're asked to find the largest number in an assorted list of numbers. So, for example, looking at the list of those 7 numbers, your goal is to turn it into... your goal is to find the largest number in the list, which in this case is the number 238. So your input is a list of numbers, which I'm going to call L, and your output is going to be that number 238. One strategy is to start with the first number, star or mark, whichever, and then compare it to the next number in the list. Now, if the first number is smaller than the second number, then we should move our marker to the second number as the largest one so far. Otherwise, we're just going to do nothing because the current marker stays with the first number, which is already the largest when we compare first one and the second one. We're going to then repeat this process by moving down the list one more number. This time we're going to compare the second number with the third number. If it turns out that the third number is larger than the second number, then we're going to move our marker to the third number. If that's not the case, then the marker stays where it is right now. We're going to continue this process until the entire list has gone through. To write a pseudocode for this, we need to have the algorithm's name, the input, and the output of your result. We're going to call this algorithm largest number. Now think about what you actually put in as an input and what would come out as an output. Well, because we're finding the largest number in an assorted list of numbers, the input must be the actual list of numbers, and the output must be the largest number in this list. To begin the algorithm, we'll start by marking the first element in the list as the largest. We'll just do a largest, which is the variable that keeps track of what the largest number is. We're going to assign that to be the first number in the list. And then for each other item in the list, we'll do the comparison. In particular, we will check if this current item is greater than the current largest item. If this is the case, then we will basically switch our marker. So we're going to assign this item to be the current largest. And I'm going to end this if statement. So always make sure you balance your conditional statements. And I'm going to end the for statement down here. In the MATLAB implementation, we're going to use a function call where the output of this function is going to be the largest. So remember, the output is included in the bracket, and there's only a single output, so you need to have a single variable there. The name of the function file is called the largest number, and remember, it takes in the input of the list in L. It's a good idea to actually include some comments that explains your input, output, and how sometimes use your algorithm for users. Once you've commented your code, you can start writing the actual content of the code. Again, just like the pseudocode indicated, we're going to initialize the largest as the first element in the code. And remember, to access the first element in a vector, you just call L of 1. And the rest of the code says, for each other item in the list, we're going to do a comparison. So for I going from 1 to the end of the list, well, that's going to be specified by the length of the list, L. And we're going to check if the ith element in the list is greater than the current largest, then we're going to swap. So we're going to assign the largest to be the ith element in the list. Otherwise, we do nothing, and you don't really have to have a piece of code that says do nothing, because remember, an if statement doesn't have to accompany with an else if. And I'm going to just end this if statement right here, and we'll end a for statement right there. And that's it for the MATLAB implementations. Feel free to actually write this code in MATLAB and run a few more, or few toy examples to check whether or not you get an accurate result. Here's another example of a simple algorithm that's going to go through the same entire thought process, where you start with a recipe and then a pseudocode and eventually implement that in MATLAB. I want you to take a few moments to try to do this yourself and then check back with me on whether or not you get something similar. I'm going to assume that I want to sort this list from the smallest to the largest. And I'm going to do this using something called the bubble sort, which is basically comparing two elements at a time and swap so that the smaller number always appears on the left in the list. For example, if my list is 51428, Then the algorithm is going to start by comparing the numbers 5 and 1. Since 1 is smaller than 5, it's going to swap the position between 1 and 5 and leave everything else unchanged. In the next step, basically copies over the same list here from the previous step here. It's going to compare 5 and 4. And since 4 is smaller than 5, it's going to swap the positions between 4 and 5 and leave everything else unchanged. So 1 still is 1, and then becomes 4, 5, and 2, 8. The next time it's going to move it down to the numbers between 5 and a 2, and because, again, 2 is smaller than 5, it's going to swap the positions. So we get the next list of 1, 4, 2, 5, 8. The next time it's going to look at the numbers 5 and 8 because 5 is already smaller than 8, so there's no swapping needed. But you notice now that this list is not completely sorted yet because, for example, 4 is still greater than 1. 2 is still greater than 4, so technically 2 should appear before 4. So what you need to do is go down the list one more time, basically going through the same process and sort it again. This time, we start with 1 and 4 again. Again, that this is already in the right order, so we're just going to do no swapping. And next time, we look at 4 and 2. We're going to swap 1, 2, 4, 5, 8. And the next time, we're going to look at the 4 and the 5. That's already in good order, so no more swapping needed. And then next time we're going to look at 5 and 8, but that's also already in good order. So that's it for this pass. Well, as we can see, this list is now sorted, but how do we actually tell the computer to stop when it's sorted? It turns out that the algorithm actually needs one more whole pass of this process without any swapping occurring in order for us to be sure that this thing is sorted. In the pseudocode, we're going to call the function bubble sort. It takes in the input L. Let's say, for example, n is the length of the list L. Then the algorithm would go like the following, which it says while swap is needed, or in more of an appropriate computer language, it's true. As long as swap is needed, that means we need to go through the list. So we're going to use a for loop to go through the entire list every single time a swap is needed. So for I going from 1 to n minus 1, and remember, you really don't need to go all the way to n because you're doing a comparison of two things at a time. So if you start with 1, then you really go to the one before it. Or if actually, because the first one, you really don't need to compare it to anyone. So it's technically you're starting with the second position in your list, and there's only n minus 1 things to check. Alright, and so for each time you enter into the for loop, you're going to check to see if the current element, the L of I, is actually greater than the next element in the list. If that's actually the case, that means we should swap. Otherwise, we don't do anything. So we're going to end this if statement right here, and end the for loop right here, and eventually we're going to end our while loop. When the MATLAB implementation, assuming that you have been listening and you are remembering to always include comments and define everything carefully, inputs and outputs, I'm going to just skip all of that stuff for now and get to the heart of the algorithm. The first step is to call in, or just to compute quickly the length of the list L. And here we're going to initialize the swapping parameter to be 1. This is basically an indicator to tell us whether or not a swap or swapping is needed. And while this swap parameter is not equal to 0, we're gonna actually go through the actual swapping or the checking of the list portion of this thing. And so for the everything in your list, going from 1 to n minus 1, we're going to check if L of I is greater than L of I plus 1. And again, this is saying that the next element in the list is actually smaller than the previous element of the list. That's why you need to swap. Now, the actual swapping in MATLAB is not as simple as simply just calling a swap. We actually need to create a temporary parameter to store the information in one of the parameters and basically do a change of variables to make things go into their right place. And that is accomplished by the following logic. We suppose that we've got Li and Li plus I plus 1. These are the two things that we have values for. We need to actually free up, because we're swapping. If you simply just let Li be equal to Li plus 1, then we're erasing the current information that is in Li, and that we can no longer retrieve after that assignment is done. So we need to free up the space by first assigning Li to a temporary variable. So we're going to let temp be having whatever the value that Li is having. And that way, that value is saved. The Li can be freed up. So this is our first step of the process. Because this position is freed up, I can now assign whatever the value of Li plus 1 to Li. Okay. And now that since the value in Li plus 1 is already stored in some other variable, I no longer need to worry about it being erased. I can assign the temporary variable, the value in the temporary variable to the variable Li plus 1. Because remember, what was actually in temp was the value from Li. So this is the third step of the swapping process. If we actually do this, then we have successfully swapped the two values. Okay, so that corresponds to, in that diagram, it corresponds to the following code, where we let temp be having whatever the value of Li is having, and now Li is free, so we can have the value of Li plus 1, and now Li plus 1 is free, so we can actually have whatever the value of temp is having, which really was what the value of Li. Okay, so these three steps right here corresponds to swapping. Alright, and every time this happens, or needed to be happened, we need to keep track of the actual swapping action. So we're going to call the swap to be swap plus 1. Because remember, currently swap is assigned value of 0. And in order to actually enter this whole while loop thing, we need to make sure the swapping is needed by adding a value to it. So now we're going to assume swap to be swap plus 1. Alright, we're going to end this if statement right here. And we're also going to end this for statement right here. Now if I go ahead and end my while statement right here, and let's check to see if this actually would run. Well, first step, swap is 1, and it satisfies the while loop, because since it's 1, that's not equal to 0, it's going to come in and execute all of this following for loop and if loop. At the end, we call swap to be swap plus 1. Well, currently swap is equal to 1, and then the swap plus 1 is going to be 2. And if we keep doing that, think about this, if you keep doing that, then your swap value is always going to be greater than 0. Then it seems to me that you're always going to be swapping constantly, regardless if the if statement is going to be satisfied or not, because we're setting the swap value to be greater than 0 all the time. So in a sense, we need to kind of reset our swapping parameter to really check whether our swapping is needed. We're going to do that by inserting one little kind of an initialization there. I'm going to set their swap parameter to be 0 here. Okay, and if we do that, then we'll only need to swap entries if the if statement part of this algorithm actually is satisfied. And that is, remember that last thing we talked about, where in order to actually for the list to be sorted, you need to have a full complete pass without any swapping. So the last step of this algorithm, you actually would not satisfy the if part of the statement, and that's when we know that the swapping is done. Because if the if part of this algorithm is never entered, then your swapping parameter would just be equal to 0, and then that would then fail the while loop. Therefore, you stop the algorithm. A very important thing to look at when we write algorithm is its stability. An algorithm is called stable if small changes in initial data produce small changes in the final result. It is unstable if small changes in the input can lead to big changes in the output. It's conditionally stable if algorithm is only stable for certain choices of initial data. And typically you want your data to be, of course, you want your algorithm to be stable. Otherwise, the implementation, it's really no use. Ideally, if the E sub 0 is the error produced at some stage of the algorithm, we want E sub n, which is the error produced after n subsequent operations, to be small as well. This is just to say that if you start with a small error, then you would expect that small error to persist through in your entire process. So for example, if C sub n is a constant for all n, and C is just some real number, and if it turns out that E sub n, which is the error at the nth step, is about the same as C sub n times E sub 0. Another way to look at it is thinking of it as E sub n divided by E sub 0 is almost about C sub n. And remember, C sub n is just some constant. So this is to say that the error actually grows linearly, because they're kind of a linear relationship to each other. On the other hand, if E sub n is approximately C to the n times E to the 0, so this C to the n is exponential behavior. So this would, in this case, we say that the error grows exponentially. Certainly, we do not want to see an exponential growth error in general algorithms. You want to stick with as small error as possible. So if you have two algorithms you're trying to write, and one is linear growth and the other one is exponential growth, then you definitely wanted to pick the linear one. And I want to illustrate the stability condition for algorithm in the next example here. The actual equations are given here. Equation 1 is given here, is a way to implement a sequence of numbers. It might not be the only way to generate that same sequence of numbers, but it is a way to do that. Let's actually look at how stable this algorithm is by evaluating just a few more terms. If you use equation 1 to generate the sequence on a 32-bit machine, then remember, in a 32-bit machine, the significant digits is about 7. So the first number, x sub 0, is going to be just 1.0000000 with the 7 zeros. And suppose we also used rounding arithmetic. The second number in the list, which is x sub 1, is going to be 1/3. But in machined precision, this is going to be 0.3333333 with 7 threes. Now this is 7 correctly rounded significant digits. For the next number, we're going to use the recursion formula, and that's x2 equals, according to the formula, it's going to be 13/3 times x1 minus 4/3 times x sub 0, and that turns out to be 0.111112, and then turns out this to actually have 6 correctly rounded digits. In the next step, x sub 3 is going to be 13/3 x2 minus 4/3 x1, and this turns out to be 0.03700373, which has 5 correctly rounded significant digits. And let's just do a few more to illustrate the point. X4, according to, again, the same equation, will give us 0.0123466. And this corresponds to 4 correctly rounded digits. And we have finite amount of patience here. So let's jump a little bit forward quickly here. X sub A actually has 0 significant digits that are correct. So that's actually 0.0003757. And none of the digits is actually correct. It turns out if you keep going to, for example, the 15th number in the sequence, we would get 3.657493. I was kind of laughing because clearly you should create a list of numbers that are getting smaller and smaller each time, but how can you actually get something that is 3.65? Also, this is totally incorrect, and turns out that this is incorrect with relative error of about 10 to the 8th power. So what seems to be the problem here? Well, because there's a lot of rounding that needs to happen each step, and we are working on a finite memory machine, and this algorithm's kind of a pitfall is because all the rounding that needs to happen in between steps, that it creates a lot of errors. On the other hand, you can actually show this by mathematical induction that equation 1 is equivalent to x sub n equals 1/3 to the nth power, which is a lot more accurate and stable. So a take-home message from this example is, when you have a choice, you wanted to implement a numerical implementations of your algorithm needs to be something that is stable. Sometimes you have choices between two different ways. You wanted to choose one that is actually stable in the sense that numerical rounding won't cause a huge issue in your final results. Finally, let's look at the big O and little o notations for convergence. In general, we want algorithms to produce reliable results as soon as possible, which means that we needed to converge to the desired solution in the fastest time. Well, when you're encountered of different algorithms, how do you actually know which one is going to converge to the solution faster? So in the industry or in the literature, people use this big O notation to tell how fast the convergence of an algorithm is. In the definition 1.3.1, we said that the two function grows at the same rate if we can represent f of x as big O g of x. If and only if there exists a large enough number m such that for any choice of value that is beyond a certain point, we have the limiting behavior of f of x and g of x the same, which means that I can bound the f of x by some fixed large constant m times the absolute value of g. Another way to look at this expression here is to simply just divide the two, and we see that if we can find an upper bound for the ratio between f and g in its absolute value, then we say that f and g have the same limiting behavior, which means that they grow at the same rate. So if we know something about the growth rate on function g, then right away we know the growth rate on the function f. It's a particularly useful notation when we wanted to look at the function's usage of its computational resources. So for example, if I'm computing something with a big O n squared convergence rate, where n typically represents the size of the list or the size of the array and the entries that are used to represent the function, then we know how fast this thing's going to grow because it's a quadratic convergence. Compared, for example, to big O n cubed, which is a cubic convergence rate, that means the big O n squared is actually going to converge to the solution faster than the big O n cubed. So in general, you want a smaller on the power in the polynomial time to have a faster convergence. But that's just an example. Next, I'm going to illustrate two examples using the big O notation. The first one is going to have basically an example that illustrates we do have a big O notation relationship in between two functions. And the second one is that we actually can't use the big O notation to describe the convergence of the two functions. In the first example here, we're going to let f of x be 6x fourth plus 2x cubed plus 5, and the second function g of x is x to the fourth. We can kind of look at visually how fast these two functions grow over time. The first function, because the factor of 6 in front of x fourth, we know its y value is going to be larger than the y value on the g for any particular choice of x. So this is going to be the f, and this is going to be the g. And we notice that as x gets bigger, particularly when it's approaching infinity, we can choose, for example, x sub 0 to be 0, and we can also choose this capital M to be, for example, 7. Then clearly, as x is greater than the x sub 0, any value that you pick that's greater than 0 for the x, we will notice the behavior that it's the ratio f over g in absolute value will be bounded by 7. And this is because you notice that if you were to take the limit on this ratio as x approaches infinity, you'll notice that the limit is actually equal to 6. You can use L'Hopital's rule, or you can simply just divide it by the largest polynomial with the largest exponent, which is x to the fourth, and you notice that this actually approaches 6. So if you simply choose m to be 7, then this ratio would approach 6, which is always going to be less than or equal to 7, which means that we were successful in finding such m, and we were successful in showing that such choice of m does give you this behavior. And so what we can say is the function f of x can be written as a big O g of x, which means that these two functions approach the solution about the same rates. On the other hand, let's look at another example where I'm going to let g of x be square root of x, which is x to the 1/2, and f to be x squared. And so what you want to see is whether or not, if you choose x to be large enough, these two functions behave the same way as x goes to infinity. By looking at its graph, we can notice that f of x is a quadratic function, so it should grow like this, and g of x, which is a square root function, should then go like that. And if you can push far out enough, you see that these two things, these two arrows, are actually not going to converge to the same directions if you choose x large enough. If you want to actually prove this formally, you have to work with the definition of the big O notation, which says that there exists an m greater than 0, and there exists an x sub 0 that is a real number, such that for all x greater than x sub 0, we get the absolute value between f over g is less than or equal to m. So if you actually want to disprove this definition, you work with the negation of the statement. So if you negate this entire statement, then we get its equivalent, which is for all m greater than 0, or for all x sub 0 real number, there exists an x greater than any choice of x sub 0, such that it's either the case that f over g is going to be greater than m, or because the choice between f and g can actually be swapped sometimes, so we could actually have this, or we can have the reverse, which is g over f, which is greater than m. So as long as it's not the case that f over g is less than or equal to m, then we're fine. So in a sentence, this means that regardless how big m or x sub 0 is, we can always find x that is greater than x sub 0, such that f over g is going to be greater than m. And in fact, this is not too hard to see. If we look at f over g, this is the expression x squared over x to the 1/2, and that is equal to x to the 3/2. And you can see that it doesn't really matter what your starting point is. Eventually, if x is big enough, this thing will always be greater than any positive real number that you choose. So this is saying that f of x certainly is not the same as g, or in terms of the rate. Therefore, I can't say that it is in the big O of square root of x. So in notation, I would write f of x is not equal to big O square root of x. We can also use the big O notation in an alternative way. And in this example here, I'm going to show that the function cosine plus 1/2 h squared, which is right here, minus 1, converges to 0 as fast as the function h to the 4th converges to 0. Okay, we're going to start with Taylor's theorem. Basically, what you're looking at here is the Maclaurin series for cosine of x, which is at basically doing an expansion at x equal to 0, and then evaluate it at x equals h. Okay, and then this is the first two terms of that expansion plus the error term of that expansion. So because we're doing evaluation at h, your c of h has to be between the point of expansion, which is 0, and evaluation of the expansion, which is at h. Okay, so if we now look at that expression and just rearrange the terms a little bit, we have the cosine of h, move this term over, so we get plus 1/2 h squared, and we have the 1 and this error term on the right hand side. If we now subtract 1 both sides to get this new expression and put that into the absolute value, we notice that this is exactly the same as the right hand side, which is this term. So that's this term right here. And because cosine of h is between 0 and h, and we know that cosine function attains its maximum value of 1 on that interval, we know this term here is strictly less than or equal to 1, which means I can rewrite this as less than or equal to 1 over 24 times h to the 4th. Okay, and so because h is a constant, and this entire thing is another constant, so what we can say is a cosine h plus 1/2 h squared minus 1 converges to 0 just as fast as h fourth converges to 0. Now I can say that because in the long run, the expression 1 over 24 h to the 4th power, when h is small, the expression actually goes to 0. Yeah, so because the left-hand side, which is this expression here, is bounded by that expression, so if by choosing h small, the left-hand side would also converge to 0 as well. Or if you actually take that expression and add 1 both sides, then it's equivalent to say that a cosine h plus 1/2 h squared and h to the 4th plus 1. You can also say that this converges to 1 as fast as h to the 4th plus 1 converges to 1 as well. So in notations, we can write cosine h plus 1/2 h is equal to the big O h to the 4th plus 1. And in words, we can say that this function cosine h plus 1/2 h has the same convergence rate as the polynomial function of degree 4, h to the 4th. Because 1 is a constant, we typically can ignore that, and then in terms of convergence rate, that 1 really doesn't do much because it's just something that's fixed the whole time. On the other hand, h to the 4th is actually a variable function that its convergence depends on the value of h. Lastly, we introduce another notation called the big little o notation that is seldomly used in practice, but it's good to know anyways. Definition 1.3.2 says the following. We say that g of x grows much faster than f of x, and denote it f of x is an element of little o g of x if and only if the limit of the fraction f over g as x approaches infinity is equal to 0. Well, this kind of makes sense. If g of x grows a lot faster than the f of x, then the denominator is a lot bigger than the numerator. The limit of that expression should equal to 0. I'm just going to give 3 quick examples using a little o notation. On the first one, if I let f be 2x and g be x squared, then obviously when I do f over g, I get 2x over x squared. As x approaches infinity, this expression actually goes to 0. So what I can say is that 2x is an element of the little o of g of x, which is x squared. The second example here, if I let f be, say for example, 1 over x, and g of x is a constant function of 1, then the limit of f over g as x approaches infinity is simply just 1 over x. And you know that this expression actually goes to 0 as x approaches infinity. So we can also say that the function 1 over x is an element of little o of 1. The third example here, I'm going to let f of x be 2x squared and g of x be x squared. And if we now take the limit of f over g, we see that this is equal to strictly 2. Now because this is not equal to 0, that means I can say that the 2x squared is not an element of the little o of, this should be 2x is not an element of little o of x squared. Sorry, this should be an x squared. Alright. And this example concludes the lesson on algorithm and convergence.